Hello, my name is Daniel. In this short talk, I'll be presenting work done in collaboration between us at the University of Cambridge and our colleagues at the University of Sussex. In the paper related to this talk, we demonstrated the use of a framework that we have developed for analyzing representations of many kinds, including natural languages, formal languages, and diagrams. The idea of this framework is that we should be able to produce descriptions of representations with enough detail so that we can compute important measures of representations that enable intelligent selection. We differentiate between descriptions and formal specification because we want to be able to work with non-formalized representations, such as ad hoc figures in a textbook, without having to first formalize a whole system dedicated to the figure. So our descriptions may lose information while containing enough to calculate important measures. So let's start with an example. Consider this problem. There are two light bulb manufacturers and they each produce defective light bulbs at a certain rate. You can pause the video if you want to read the full problem. To solve the problem, we can reformulate it in a formal language for conditional probability. We denote the manufacturers by A and B, and we denote the events of getting defective light bulbs as D1 and D2, and so on. But we can also represent the events as regions in the plane where their areas are proportional to their probabilities. Then the problem becomes one of calculating the ratio between two areas, in this case the patterned area against the shaded area. So here we have two representations of the same problem. So what can we measure out of them, and how can we even begin to compare them? To answer this, we first need to be able to talk about them. So we developed a language for describing representations. This language allows us to encode aspects of representations at various levels. For example, we can encode the atoms of a representation, which we call tokens, and we can encode syntactic structures through what we call patterns. They tell us how things come together to form more complex structure. For example, a pattern associated with a token for probability tells us how this token forms part of expressions of greater complexity. Moreover, in the geometric figure, we have atomic regions which can be considered together to form a region that represents the union. So if we have already descriptions of representations and we want to solve them, so we want to be able to compute certain measures. So as a proof of concept, we have developed two measures and implemented them. One is a measure of informational suitability, which aims at comparing representational systems according to whether one or the other is more likely to be able to represent a problem and its solution. And the other is a measure of cognitive costs, which aims at estimating, given a user profile, how it can be used, how costly it will be to process various aspects of the representation. So ultimately, our goal is that with measures such as these, we can recommend representations to users of tutoring systems or of proof assistance, and this is all ongoing work. So to summarize, our framework includes a language for describing a variety of representation and methods for obtaining informational and cognitive measures from their descriptions. And in future, we will try to operationalize the process by creating a description given an arbitrary representation, either for human analysts to be able to use our framework or to actually automate the generation of descriptions. And moreover, we are developing user profiling tests to feed into our cognitive costs calculations and empirical studies to test how our results compare to expert representation selection. Thank you for listening.